Hi everybody, thanks for having me here. As already has been said, I'm a postdoc at the Vision for Robotics group. We are working on the intersection of computer vision and robotics. Currently I'm doing some research internship, or let's say research exchange here with Jose Garcia, and I think that's also the reason why Jose invited me to present here. I just finished my PhD last year, so he thought it might be interesting to show you what I did and how I presented my thesis, maybe to give some example, and probably also on the other hand, because it's quite convenient probably for him to just ask me instead of writing people and trying to get them here. So yeah, I'm going to talk about my thesis and also try to give some more information on the background regarding object pose estimation and object detection, stuff like that, and how it's connected to robotics. Yeah, that's the agenda for now. Just going to start with motivation, to have a general overview, a little bit of problem description for people working in other fields, and also I introduce the pose estimation formulation, how it's handled with neural networks. Then I'm going to talk about my methods. And afterwards, I'm going to give a quick summary on the outlook, what we're currently working on. So, what's the motivation? Yeah, like the real world consists of a plethora of objects. You ideally want to handle all of them without having to train every time for hours or days. And especially what you don't want is annotate real world data. So you don't want to go out there, capture the object you want, get a mesh, annotate the object in the image, capture a whole scene, go to another scene. You kind of like get a lot of biases regarding the illumination, the position, the camera intrinsics, and so on. So the nice thing to have is some automatic system, creating a training data, training a network, going towards deployment. For stuff like bin picking, mobile manipulation, augmented reality. There are a bunch of problems that are usually addressed in the computer vision community that are way more important for them. Computer vision community always tries to maximize the performance on datasets. Datasets are rather narrow, and often it's kind of like not feasible to also apply these algorithms then in the real world. So for robotics, there are some other things quite interesting, as for instance, deploying stuff in unknown domains, handling multiple objects at the same time. I'm going to come later to that specifically, why that's important, and also multi-instance handling. I also include inferring poses of novel objects there. That's what I'm currently working on. I should probably not undisclose this because it's quite possible that if I send it somewhere that one of you is the reviewer or something like that. So it's probably not good to actually include it there. I still have it there. Yeah, so what's the main problem of object pose estimation as compared to 2D localization? So 2D localization usually refers to object detection. What you usually want to have is the upper left corner in the image of the object, of the bounding box of the tightest rectangular bounding box around the object, and the lower left point of the bounding box, right point, sorry. This leads to a few things. So what you need to be equivariant to is actually just the 2D translation in the image space. What you can safely disregard when it comes to learning is the rotation and stuff like symmetries. For 6D localizations of object pose estimation, it's a little bit more complicated. So you need to infer the 3D translation, the 3D rotation. Obviously that's also depending on the intrinsic, so you usually want to have a rectified camera to simplify stuff. And also you need to be aware of the symmetries of the object because that's detrimental to convergence of a network if you're not handling that carefully. Yeah, so you see 6D localization is already a quite more complicated task than 2D localization. So one thing that would be nice to have is having like that simple inference that you have for 2D object detectors, which are usually trained for multiple objects, for multiple instances, have kind of like a constant runtime, independent of the number of objects in the image for the 6D localization. But there are some tasks that need to be tackled in order to gain that or to achieve that. So the things I was working on is how to get stuff to novel domains, how to do it simultaneously for multiple objects, and how to get it scalable with respect to multiple instances of the same object and of multiple objects, obviously. So that's the work of a colleague of mine. It's Pix to Pose. It was quite well received by the community. That's like the standard case how the computer vision community views object pose estimation. So you have a first stage where you're detecting the object with a 2D detector. You get sparse location bias in the terms of bounding boxes around the object, as you can see in the leftmost image. Then you have a second stage, which is the object pose estimator. In the meantime, it started to shift, and people try to get it running for multiple objects simultaneously, or just train one network for multiple objects. But the standard case is still that you train one network per object of interest. So if you have, obviously, kind of like I don't know, that's the line-mode data set. More specifically, the line-mode occlusion data set, which is a subset of line-mode, which has 13 objects of interest. So if you train for line mode, you're training 13 networks just for the object pose estimation part and one network for the detection part, which also, quite obviously, if you want to get that working on a robot where you have limited memory and limited resources, it gets quite infeasible, quite soonish, and relatively soonish when it comes to the amount of objects you want to handle. And since it has been shown that direct 6D pose regression doesn't work so well, the standard case nowadays is to regress geometric correspondences in terms of UV coordinates, as you can see here in the second most box to the left, or key points. And then use EPMP or something like that to estimate the rigid transformation between your 2D correspondences to pre-computed 3D correspondences. A little bit too much into detail, I think. Anyways, so talking about pose representation. People really like to use UV coordinates because you get a quite large hypothesis space. So if you look at the upper right image, you see basically for every pixel in the query image, you get a color, a three-dimensional color vector corresponding to the location of that vertex on the object surface. Another quite often used representation, what I usually was using, are key points. You define just a sparse set of key points or locations in the object coordinate frame and project it to the image, and basically train for predicting these locations independent of a certain object. So if you look at the numbers here, so I'm presenting my main three methods are SID-Pose, Pyropose, and COPE. With COPE I end up having an output space, so I throw an RGB image at it, and I get an output space of 108,000 locations, corresponding to image locations and key points per location that are predicted, which ends up being approximately 500 megabytes on the GPU. If you look at the UV coordinates and what Pix2Pose is using a detector, a retina net, which already has, I think, 300 megabytes. Then you have one network trained per object of interest, which is ResNet50 encoder plus a mirror decoder with the same number of parameters. ResNet50 is approximately 200 megabytes plus the decoder, another 200 megabytes. You have 400 megabytes per object of interest. So if you're now doing inference on the line-mode dataset with 13 objects that are being used, you end up having 5,200. So 5.2 gigabytes plus the object detector 5.5 gigabytes. That was 2019. Getting that thing running in a robot is quite infeasible actually. Yeah, and as I already said, both things work the same. You're regressing the geometric correspondences, key points and UV coordinates, and use some old method PMP or some modification of PMP to infer the pose indent effect for each object. So you have different stages that obviously end up being not scalable in the end. So here's a quick interlude why symmetries are problematic. So you can see on the left side you can see continuous symmetries, on the right side you can see discrete symmetries. The problem with continuous symmetries is you can basically rotate the object around the axis of symmetry, and you end up always having the same view. So your network doesn't have the information to disambiguate these views. However, you're always passing a different pose based on that rotation to the network. That is a definite convergence. So you need to handle that case. And on the right side, you see discrete symmetries. It's similar, but you don't have an infinite number of views around the axis of symmetry. What you rather have is a discrete set of transformations that end up viewing the same or supposedly the same view of the object. So, at first I'm going to talk about some synthetic data generation for object detection and pose estimation, and also pose estimator for multi-object pose estimation, and also only train on synthetic data. So, classical pose estimation methods kind of like need no training data compared to deep learning methods. You have a mesh of the object. You're just rendering different views of that one mesh. You encode some template, some lookup table, and during runtime you compare similarities of what you're observing to that lookup table. The nice part here is you kind of like have no domain shift. I mean, you sure have some domain shift, but you don't necessarily have a training domain or varying test domains. You have a training domain, but everything that is the test domain is known. You don't have varying test domains. So that's quite nice. That's also what we want to achieve in deep learning. We were using depth data there because it has been shown that domain adaptation in depth data is easier because it's just a more limited domain than RGB. However, I will also come to that point later where I explain that that's actually kind of detrimental in some cases. Especially talking about symmetries and stuff like that, because you quite often have objects that are symmetric, where the mesh is symmetric, but on the other hand, you have texture that is actually disambiguating these symmetries. And we also want to perform multi-object handling, and we use, obviously, geometric correspondences to improve our direct pose regression. So, the training data is simply generated by having three sets of objects. We have static background object, random background objects that you can also call distractor objects and objects of interest. You just throw them in the synthetic scene, randomly sample the camera, capture the depth maps and visibility masks, because that's specific to that sensor that I was using at that moment, and then you augment it. And so you get a randomized domain that is quite similar to the real-world domain of the sensor. So here's the depth data generation more in detail. It's basically about, you have those infrared light sensors where you project the infrared pattern to the scene. Then you have a baseline, with a small baseline, the sensor, who is capturing the pattern and calculating the depth data. What you usually get is you get some occlusion of image regions based on that baseline. So we're simulating that here to be closer to the real case, and also to simulate the influences of illumination changes, because those missing regions get bigger if the illumination is higher, or if you have more challenging material properties. And we're rendering that whole stuff, getting depth data, getting the visibility mask, and getting object masks and obviously poses. Then we use depth data augmentation, where we randomize on the one hand in terms of the sensor model we're using, something similar to the sensor we're using, and we also apply quite general noise characteristics, so to say the Gaussian noise, which is usually used for creating realistically looking, for instance, mountain chains and so on in computer games. And afterwards we color code the images based on the normal direction. So, the first thing we did test it on, I'm sorry, that's probably quite boring in depth. I try to pass fast over it. We did test it on fast RCN for object detection. The nice part of line mode is actually that there's a second set, the occlusion data set, which features 8 objects of line-out data set. So you have 1,214 real-world samples of these objects. You can train on them and compare it to training on synthetic data with the same number of objects. And we actually achieved better performance than with the real samples. Why? Simply because the data is better generalized, better randomized. Sorry. In terms of generality, we have a more uniform distribution of camera viewpoints, a more uniform distribution of occlusion patterns, of object poses, and so on. That's an indicator why using synthetic data for training and not real-world data is better if you're able to properly close that domain gap between training and test domain. So, here on the other hand, we have some error cases that are coming from the random process and also from depth data. You can see in the left image, there's the benchwise and the duck sitting on the benchwise. That was purposely placed there by the guy who captured the data set. However, that's a case that object interaction is actually not happening when randomly sampling locations in the synthetic data or during synthetic data generation. So it kind of shows that it's probably not the nicest and most general thing to do, or data was too little probably. And on the right side, you can see unknown objects that are similar in geometry. So the bowl, you can see in the left image on the top, it's a white bowl. So the geometry of the knee of the guy capturing the data set is apparently quite similar to the bowl. However, if you would have used color data, you would see that, or the estimator would see that it's obviously not the same object. However, you still get the misdetection because we're just using geometry priors. So probably it's better to use RGB data in the future. We also applied it to object pose estimation. We did modify a rate in the net to have a key point head for multiple objects, and we did extend 3D bounding box estimation. So here's a small interlude for object detection, since I guess most of you are not working with object detection or pose estimation, stuff like that. You have an input image. If you look at feature pyramids, you have an input image, and it shows that the divide and conquer strategy of feature pyramids are really great for object detection. You get the input image, pass it through your backbone, have different feature maps at different resolutions. You're sampling anchors in these feature maps, and so based on the size of the object, you're estimating the location of the object based on its size in different resolutions of the feature maps. Here are also some anchor parameters. It's probably too much in depth, but still useful if you want to know it more in depth. So what we did adopt that anchor sampling scheme from object detection for pose estimation. We sample image locations and bounding box sizes based on anchors, standardize our key points for object pose estimation with these anchor parameters. We then in the end get, during testing and during training and during testing, a hypothesis space of class, bounding box, and key points. We apply non-maximum suppression during testing and infer poses using Ransack EPMP. Non-maximum suppression is also something coming from object detection. You have a bounding box, or let's say you have, in that case, in that small example, you have 3 bounding boxes, two of the type of object blue, one of the type of object red. Non-maximum suppression is just filtering the bounding box with the lower detection score based on an intersection or a union ratio, and retains the one with the higher score. Obviously not filtering different objects of different classes. What we ideally would like to have is something similar to recent developments for object detection, which are generalized or intersectional union losses. If you look at that green, is it yellow or green? Anyways, if you look at the leftmost thingy there with the red bounding box and the either yellow or green bounding box, sorry, I'm colorblind. It's weird that I'm working on RGB and I'm colorblind, but it's like that. I can change it. You've got the L1 loss or L1 or L2 loss, let's say of 9.07, and the same applies to the middlemost field. Even though you can visually see that in the middle the intersection of a union is higher. So that means L1 or L2 loss are not the best losses to apply. So that's why people came up with intersection of union losses directly for backpropagating or for calculating the loss, or generalized intersection of union. Also what I want to show, I was using the Huber loss. The Huber loss is also quite nice. It's in general a quite nice loss. So if you're thinking about calculating losses and backpropagating the loss calculated, the L1 or the L2 loss, don't do it. Use the Huber loss. It's less sensitive to outliers due to the L1 characteristic further away from the optimum, and it has a smooth transition to the optimal value near the optimal value, so the characteristic of the L2 loss. Anyways, we're using the Huber loss, and we want something like that for our 3D bounding box, like the generalized intersection over union loss. So, in the beginning, what we did from our object handling is we separated the last convolution layer to have specific weights, specific output parameters for each object's key points, which helped us getting more scalable or improving performance for multiple objects on the one hand. And on the other hand, we also applied some consistency in 3D space, making sure that those edge length differences of the key points, or of the edges between key points projected to the image space, are similar for the ground truth and the estimate, in order to properly backpropagate, kind of like 3D heuristics in the 2D space. So, the takeaway is what we actually want to achieve. We wanted to get close to the performance of classical methods like, for instance, PBF by Trost, which just takes the object mesh as input. So we also only have the object mesh as input, using some standard metric of object pose estimation, which is the L1 score. We're not even close there because it's just considering the accuracy, but however also including the recall rate for pose estimation, so to say using the F1 score of the metric, we outperform Trost. That Trost needs like an hour to train for a data set, and we need 2 weeks. Don't talk about it. It doesn't matter. The detection performance is also quite good. Yeah, it's just showing the orthogonality constraint is improving things, and also the multi-object pose estimation formulation we have is quite similar to actually training separate methods. So, what we showed here also is that depth data is probably not the best thing to use for pose estimation and for disambiguating the complex observations that are necessary to infer 6D poses. So we tried to generalize in RGB. So it has been shown that feature pyramids generalize well in the RGB domain for object detection. We were already using feature pyramids, so why not further use it? And also, we want to improve the object detection and pose estimation, the simultaneous stuff, for typical scenarios. So what we did experiment a little bit with the key point head. Turned out we don't need those separate weights in the last layer for multiple objects. All that we need is surprise and more parameters. And also we did play around a little bit with backbone freezing, augmentation, stuff like that. And we also predict the mask to have some more information of the relevant object locations to improve performance, refining stuff with ICP and stuff like that. So we came up with a feature pyramid network because during that time it has also been shown that deep aggregation of lower levels are quite nice, because you also want you don't want to just estimate big objects with very meaningful and very abstract features. You actually also want to estimate small objects with meaningful features. So you want to process lower levels of the feature pyramid more. Also for object pose estimation, usually the scale is way less than, or the depth difference, the depth variation of the object with respect to the camera is way less as for object detection. So maybe we don't even need all those high or abstract layers for pose estimation. And also, lower levels of the feature pyramid, a higher resolve, does increase the hypothesis space, which is also always kind of nice for object pose estimation. And we also tried to get the thing in RGB running or working just from synthetic data. So we did it with a few small changes. So for instance, we froze the first two stages of the backbone. We need the third stage unfrozen so that it can somehow adapt to the objects we want to estimate. Otherwise, during fine-tuning, we don't learn features for these objects. In our case, we actually observed that batch memorization doesn't give us much. Actually, it's detrimental in that synthetic to real case, or in that strong difference of domains. And we also applied some more diverse augmentations, so to say, diverse contrast augmentations, because that's also a thing that during rendering, you also always have those sharp edges and that nice contrast. You don't want that actually, so more augmentations are always good, like parameters always good. Yeah, I skimmed through it quickly. We showed that on line mode it's working better than most of the standard approaches. We also showed that on the occlusion data set it's working way better than most of the standard approaches. Where CDPN and Pix2Pose are actually like having separate networks for detector each object of interest, and we are just having one object for the whole data set, so for all objects of interest and for detection, for estimation. I have to add, Pix2Pose and our methods is using here the same training data. CDPN isn't. CDPN is using some inferior training data there. More interesting is that you can show that Homebrew database features 3 objects of line mode with different data characteristics. So it's 3 of the objects. You can see the bench files on the right side. The mesh is different. What you can see here is that the topmost part is rotating in a different direction and the backmost part is rotating in a different direction. So there are small differences in the mesh that are used for creating and also in the objects used for testing. And also there are strong variations in terms of object placement, object interaction, illumination and other characteristics. And you can see on the rightmost part that our method there is actually quite nicely transitioning the performance from the line mode dataset or training on the line mode dataset also to the Homebrew dataset without retraining. So we showed that it's also working quite nicely, almost without a loss in performance in an optimum. Yeah, forget about the evaluation. It's not too important, I guess. The rightmost part shows an image of our method where using it on an object is actually meant to be reconstructed for in-hand manipulation from a project that we did back there. It worked quite nicely. And unfortunately, we didn't get a paper out of it because the colleague left university and went to industry, but it was quite a nice project, and I just want to show the video. So here's a small interlude again for grasping. I think I saw some posters about grasping. Anyways, like, usually what you're doing in grasping is, DexNet was a very famous paper, and DexNet 2 as well, where the people tried to transfer grasp points, so they had like a plethora of known objects where they had grasp points, and they tried to generalize with training on these grasp points to novel objects. Works quite well. Is kind of like that robotic thought or the robotic sense that you don't want to retrain for every object. Really nice. We also did, like colleagues of mine also did similar things with experience-based grasping, so they had a bunch of objects where they annotated the grasp points. And try to iteratively transfer those grasp points to similar objects. Also works quite nice. But in our lab, we actually want to manually annotate grasp points. Sounds stupid, but there's a simple reason to it. you don't want to grasp that thing on top. So if you learn to just generalize grasping, there are usually like some kind of semantics or affordances, also considering like classes and so on. You want to have specific grasp points where you want to grasp a specific object. So we manually annotate grasp points. That's why we also need the object pose estimation to infer the pose and then transform the grasp point to that pose to grasp the object. Here you can see an example on the bottom. Oh, sorry, I want to show the video actually. Oh my god. So that's the experience-based grasping thing where where colleagues of mine iteratively transfer grasp points of known objects to unknown ones. Doesn't give much away. Better read the paper if you want the insights. Anyways, bottom part you see the leftmost image is the estimated pose. The middle image shows the annotated grasp points, and the right image shows grasping the object. We also did it. Oh, come on. So we also did evaluate our object pose estimator that was trained in the synthetic domain for real-world grasping, and it also showed that it quite nicely generalizes to the real-world domain on a robot or in a scenario never seen before, for a camera with unknown intrinsics, stuff like that. Oh, sorry. Okay, great. We've got that multi-object thingy going. We've got the domain generalization going. Most of the things are covered. In the meantime, there were methods published that showed that anchors are nice. They are like one quality measure, one quality feature of object pose estimation, but it's actually inefficient because you got quite a lot of object, quite a lot of image locations, so quite a large hypothesis space. And so what you actually can do is reduce the output parameters by having some anchor-free design, increases convergence, reduces training time by reducing the output space. And we also actually would like to get as scalable with pose estimation as we are with object detection. So we want to get rid of the PMP stage because it has to be done for each object instance separately. We want to do it in parallel. So that's our method code. We use the key points as an intermediate representation. We have a small head that is sliding over that intermediate representation of key points and inferring poses for each of the image location, kind of like parallel. So, probably too much into detail. No anchors. Important part. Yeah, there are some things that we have to get going in order to actually train on the key points and also train on the pose simultaneously, as for instance symmetry handling. While it's quite easy to have the lookup table for the key points to only backpropagate those key points that lead to the smallest loss, we also had to pass an indicator function to the head network so that these two are not working against each other. And during inference, we just simply cluster similar objects using intersection over union, kind of like the inverse strategy of non-maximum suppression, and we average over the n-pose hypothesis with the highest consistency. So, yeah, we are not on par with multi-model formulations that are present before, but for single model formulations, we are, in some cases, we outperform the state of the art and some not, but the important part is we are way faster, and compared to those multi-model formulations, we are also quite scalable, which is quite nice. We also show that having an intermediate representation and the learnable PMP improves performance quite a lot to key point regression itself. And we also show that our method is quite scalable, up to approximately 90 object instances in the image. So we also did experiment with transparent objects. Let's call it partially transparent objects. Also works quite nicely, at least here. In fact, it's not the case. So that's something that we're currently working on more, going in the direction of estimating poses of not just opaque objects and heavily textured objects, but also objects that have more challenging material properties. We did some evaluation on grasping that semi-transparent thingy. It doesn't work too well from RGB alone. So that leads us to actually the outlook. One thing, transparent objects. Transparent objects do not work nicely in computer vision. So we're working on transparent objects currently. Also, rendering data, having a lot of training data, is quite nice. It takes time. So what would be really nice is to have some self-supervised stuff, because self-supervised learning has been shown, especially with vision transformers, to generalize quite well. So what we actually would like to do is maybe have a bunch of objects that we know and use self-supervised learning to learn a more general representation. Maybe also do like object pose estimation, a completely novel object that we've never seen before. And we are also currently experimenting with texture agnostic stuff, because it has been shown that while, for instance, vision transformers are rather texture agnostic, CNNs are rather texture biased. So maybe it gives something to try to get or to have texture agnostic CNNs in terms of performance. And also, did one of you guys ever work with objects and trying to reconstruct objects with a texture? It never looks good. You always have a lot of noise in the texture, and it would be really nice to not need the texture, because creating CAD models or meshes of an object is comparably simple to creating a measurable object with a texture. Sorry, one last advertisement. We are having a conference in Vienna, so if you ever were considering becoming to Vienna and getting that paid by the university, consider submitting a paper there. It's only rank C. It's still a major conference, just if you're interested. Thanks for your attention.
Any question? No? Thank you very much, Stefan, for your presentation. I would like to know, I would like to ask you two questions. Maybe the first one is more technical, and the other is maybe another related to the students. So thinking on the technical question, what do you think are the open research areas related to pose estimation according to colors? You said that agnostic texture could be an area of interest.
It's not a big option, open thing. So looking at the state of the art, the big open things are actually like transparency at the moment, and novel objects. So for 2 years now, there was an increasing number in publications in CVPI, ECV, ICV, ECV that was actually going away from instance-based object pose estimation over category-based object pose estimation, which was quite a thing since, I guess, 2018, something like that, or 2019, toward estimating poses of completely novel objects with template-based schemes.
Perfect. So
those are the really big things.
A lot of research related to the texture. So that's what you said, transparent. You say also maybe specular objects could be also difficult to grasp. And do you think also related to the kind of the object, how we're going to grasp the object? is any interesting area to do the research, because I think it's not the same if we are going to use the microphone to talk or the microphone to hit something. Maybe we grasp the microphone in different ways.
Yeah, exactly. So I guess affordance-based grasping is always quite interesting. I'm not fully aware of the state of the art when it comes to grasping. I never really worked on it. Colleagues of mine worked on it, but I guess it's just a guess that looking for things how to generalize affordances to normal objects is probably quite interesting and most likely very unsolved.
Okay, thank you. And the other question I think is more related to the audience, because you were talking about a lot of models related to deep learning.
Yeah.
I think you said we're training for 1 hour, 2 hours instead of weeks. I think you were joking or something like that. So maybe I think a lot of students are working now in deep learning.
Yeah.
So we know that we waste a lot of time training the networks. And maybe later we change a variable, then we have to change everything. We have to wait for weeks.
Again,
maybe you have to go some tips related to your experience with that kind of models.
So I recently started working with vision transformers and tried stuff like novel object process estimation. These things are actually quite fast. So what I did train recently was a vision transformer on a limited set of objects and tried to generalize it to a similar but not the same set of objects, and the training time was a few hours, probably 2 or 3 hours. And then anyways, like looking at vision transformers already generalize quite well without even fine-tuning them. So since the features they learn are quite general, especially pre-trained on ImageNet, you can already get quite good estimates if you have a suited matching strategy of views and so on, without even having to retrain. So that's probably also quite interesting.
Thank you very much, Stefan.
Thank you for the questions.
Yeah, Dimitri?
Hi, Stefan. Thank you for an interesting talk. Few interesting ideas we've heard today. My question to you is, do you think we need to update the algorithm or the network to grab small objects? Because what we've seen so far, those are objects bigger than...
Yeah.
But small objects, I think the error is propagating more, maybe? So what do you think? Should we change anything on what you've shown?
So, I mean, in order to include that, I, for instance, had that I was using a shape prior to scale the loss based on the based on the expected projected object extent, which is also helping a lot to improve performance for small objects. But I think you were also talking about grasping now. That's solution for object pose estimation. Grasping small objects is probably anyways quite difficult because you tendentially have a large error of a small object compared to the object size, and also grasping small objects requires a specific reference.
Okay. Okay. Thank you.
Hope that answers the question.
Yeah. Thank you.
Thanks for the question.
Any other question?
Hello. So far we saw that you concentrate mainly on the visual spectrum of the light.
Yeah.
If you try to increase the spectrum with, let's say, thermal or ultraviolet, I think it could help a lot in detecting transparent objects due to different refraction index of the surface.
It does. And didn't work with it. I know a few papers that are going in the direction of using RGB plus, what was it? It was some other spectrum for detecting objects, for detecting transparent objects and estimating the poses, and it definitely does help. However, I personally feel like using RGB cameras are everywhere, are in the meantime quite cheap, easy to employ, easy to apply everywhere. It definitely has validity to use in maybe an industrial setting or in a general robotic setting, different spectras. However, I personally quite like RGB cameras. I also don't like depth cameras too much. They are quite noisy. Each camera has a specific camera characteristic based on the sensor characteristics, stuff like that.
Yes, thank you.
Thanks for the question.
Thank you, Stefan, for the presentation. Could you go back a little bit in the slides? A little bit further. This one. So
this
here
one?
you mentioned, yes, this one.
Yeah.
So here you mentioned the success rate,
Yeah.
60 and 70%. This is the success rate with the complete system. So the post estimation that you made plus the robot, right?
Plus the grasping, yeah.
How far was the robot grasping the parts from where you estimated to the reality? So was the robot grasping in the same position, or there was some kind of error when?
Are you talking about like the grasp points that were annotated? I didn't evaluate it.
Okay, okay.
To be honest, it was for robotics conference. Robotics people like robotics experiment. It was an additional experiment to show that you get it in robots running, you get the paper accepted.
Okay. Thank you.
Thank you for the question.
Thank you. Other questions? No? Okay, thank you very much for your presentation, Stefan. Thank you.
Thanks for having me.